Hey everybody, we're talking about equivalent representations in binomial theorem today in section 11A. So let's jump into it. So when we're given a polynomial function, there's a bunch of different things that we can get from that information. So for example, when it's in factored form, we can see both zeros and the multiplicities of the zeros. Right? If I set these equal to 0, we would get x equals -5 and -2, and then their degrees on each of them tells me how many times it happens at that 0. If it's in standard form, the degree is something that we can know, right? The degree tells me a couple different things about it, how many zeros there are, as well as possibly how many different directions it can go. We can also know the y-intercept. If you notice, if I plug in x equals 0, the answer ends up being just this constant term. So that's our y-intercept. If it's in standard form, we can always see that. If it's in factored form, we can also find the domain by setting the denominator equal to 0. We can find the wholes by looking for common factors. We can find the zeros by setting the numerator equal to 0. And we can also find the vertical asymptotes by looking at the denominator that is not a whole. Also, if it's in general form, we can also know the horizontal asymptotes by comparing the degrees in the numerator and denominator. This one would be that y equals 0 because the denominator degree is bigger. We can also know what the y-intercept is. Remember, the y-intercept is when we set x equal to 0. And in this case, it would just be the constant term over the constant term, which would give us our positive 4 y-intercept. And then here, for example number 2, if I'm looking at this one, actually let's fill in example number 1 first, sorry. So this is in standard form. If I went ahead and factored this out, I can see all of these have a common factor of 2x. I end up with x squared minus 8x plus 16. I can go ahead and factor this down to what multiplies to 16 and adds to -8. We've got -4 and -4. So we end up with 2x times x minus 4 and times x minus 4 again. So a couple of things. What's the degree? Well, the degree we know is from that general form is 3. Remember that if we're looking for end behavior, this is from way back, this is going to be positive and odd. So positive and odd means we're going to go up to the right and opposite on the left. So the limit as x approaches -infinity is going down, where f of x is also -infinity, and the limit as x approaches infinity, f of x is going up to infinity. To find the y-intercept here, remember the y-intercept is when x equals 0, so I plug everything in for x. Our constant term is also 0, so we say it's at 0. For our zeros, we're going to set each factor equal to 0. So I get 2x equals 0, and x minus 4 equals 0, and then x minus 4 again equals 0. So we get x equals 0, and x equals positive 4. And if I want to know where x is greater than 0, remember that's when we would sketch this. So I know my zeros are at 0 and 4, but remember this 4 has a multiplicity of 2 here, so it's going to bounce from it. Our end behavior is left and up to the right, and so we see it looks something, it goes through the 0, and it bounces off 4. To see where it goes greater than 0, it's going to be all of this above there. So we get from 0 to infinity. All right, so what about example number 2? It's a rational function already in factored form for us. So our domain is when we set the denominators equal to 0. So we know x cannot be -3 and 1. So we know that's from -infinity to -3, and then from -3 to 1, and then from 1 to infinity. Our zeros are where we set the numerator equal to 0, so x equals 0 and 5. Wholes are where we have common factors. In this case, there are none. Vertical asymptotes is where we look at our denominator. Often it's like the domain as long as there's no wholes. So again, our vertical asymptotes are x equals -3 and 1. Our horizontal asymptotes is when we compare the degrees. So we're going to multiply 3x times x in the numerator and x times x in the denominator. I see that we have the same degrees. So what's left is our leading coefficients, which is y equals 3 over 1, which is just 3. And for our y-intercept, we're going to be looking for, okay, if x equals 0, how do we find those values? Well, I know here on the numerator, we're going to have 0 times negative 5 all over 3 times negative 1, and we end up with 0. So our y-intercept is 0. All right, let's talk about something new. It's called the binomial theorem. Okay, so binomial theorem is really, really helpful when we're multiplying out binomials. You'll see this before, that we're just factoring. So this is like just saying x plus 5 times x plus 5. If we FOIL this, remember we go first, outer, inner, last, we get x squared plus 5x plus 5x plus 25. If I combine like terms, we get 10x here. Okay, so we're used to that. Well, what if I wanted to do x plus 5? Well, I know I'm going to multiply that out. 3 times x plus 5 times x plus 5 times x plus 5. Well, I already know that x plus 5 times itself is this. So I'm going to put this here, x squared plus 10x plus 25. And if I multiply it times that x plus 5, we're still going to need to distribute out, like, or what I call is FOIL plus, to each of these terms. And we end up with x squared times x is x cubed, x squared times 5 is 5x squared, 10x times x is 10x squared, 10x times 5 is 50x, 25 times x is 25x, and 25 times 5 is 125. If we can clean that up a little bit, we end up with x cubed plus 15x squared plus 75x plus 125. Okay, so there's x plus 5 cubed. And now you're thinking, no, I don't want to do this again for 4. So I'm going to show you an easier way to do a binomial expansion by any value. Okay, and this is called Pascal's triangle. So Pascal's triangle depends on the degree that we're dealing with. So we can have a 0 degree, that's x to the 1, 1, 2, 3, 4, 5, and 6. Okay, and Pascal's triangle looks like as you might have expected a triangle. So in the beginning, we start with a 1 right in the middle because anything to the 0 power is 1. And then from there, along the edges of Pascal's triangles, there's always 1s on these diagonals. So, and then from there, we're going to add the sum of these, and it's going to become 1 plus 1 is right here is a 2. Okay, so we add the sum. And then once we have the sum of those middle numbers, the 1s are on the outside. So let's do that again. So we're going to add 1 plus 2 is going to go right here. We know that's 3. And then 2 plus 1 is also 3. And then when there's nothing else, we know the outsides are 1. Do you see how this is kind of starting to make a triangle of 1s? Okay, so let's keep going. I know 3 and 3 is 6, 3 and 1 is 4, 3 and 1 is 4 again, and then we put our 1s on the outside. Do you see how the triangle keeps getting wider and wider? So we know the next number here is going to be 1. 1 plus 4 is 5, 4 and 6 is 10, 6 and 4 is 10, 4 and 1 is 5, and then we put a 1 here as well. To find the 6th degree, we take 1, add the 1 and 5 is 6, 5 and 10 is 15, 10 and 10 is 20, 10 and 5 is 15, 5 and 1 is 6, and a 1 again. So here's what this does for us. Notice here that before, when I had x plus 5 squared, that would have been this row, okay? So let's call this is our first term and this is our second term. So this would have been x and 5. Okay, so what you're going to do is you're going to take every term and we're going to start off with this is 2. And then the sum of the exponents is always going to be 2. So then this one's going to be x and 5, where this is 1 and 1. And this is going to be x and 5, those 2. And then instead of going 2, 0, 1, 1, this will be 0 and 2. Okay? So the first term is going to be decreasing. The second term is going to be increasing. Notice what this turns into. X squared times 5 to the 0 is just x squared. We see it right here. X to the 1 times 5 to the 1 is Oh, sorry, there's a 2 here. This is the coefficient. Here we go. 2 times 5 is 10, so that's our 10x, okay? And then x to the 0 is just 1, and 5 squared is 25, so this works out. So let's see how this works for 4. So here we go for 4. We're going to put our coefficients here, which is 1, 4, 6, 4, 1. And then you're going to put your first term, which is x. You're going to put 1 on every single one here. And then your second term is going to be 5. We're going to put them about right here. Okay. Now, you're going to go through, and on every first term, we're going to put our biggest number here. So 4, and then this one's going to have, it's going to go in descending order. 3, 2, 1, and then 0. Wait, where'd it go? 4, 2, 1. And then there should be another one right here. This will be 1, 4. Oh, sorry, I messed up on this one. This is where I messed up. See? I knew I messed up somewhere. There shouldn't be 2 3s. Try again. Okay, so this one's also a mistake. Okay. Here, I'm going to put my 5 back here. Here it is. Okay, so we go 3, 2, 1, 0. And then on the second term, we're going to start at 0 and then increase until the number that we're going for. Oh, except for I did it wrong again. Oh my gosh. Hold on. Go back. All right, try again. Here we go. Here's our 4. So 0, 1, 2, 3, and 4. Okay, so now we're going to put pluses in between each one, in between each, and now we're going to evaluate here. So I know 1 times x to the 4th times 5x to the 0, that's just 1. This is x to the 4. Here we get 4 times x to the 3rd times 5. 4 times 5 is 20, x to the 3rd, plus 5 squared is 25 times 6 is going to be, what is that? 150 times x squared. Here, 5 to the 3rd is 125 times 4 is 500 times x to the 1. And then lastly, x to the 1 is just 1, so 5 to the 4th is 625. And this is doing it without having to multiply it out 1 by 1 by 1 by 1. So if we know our coefficients, we can find our terms first and second and put them to a power. It can simplify this a little bit. So for example, number 3, let's see what this is, okay? So if we're going to the 5th power, we're going to use this row of coefficients. So 1, 5, 10, 10, 5, 1. And remember, this is our first term, and here's our second term. So we're going to write our terms here first on every single one. And then second, put it in a parentheses on every single one. And then now we're going to put those degrees. So starting with the first one, we get a 5, and then we go 4, 3, 2, 1, 0. And then again, starting on the left side, our second term starts at 0, and it increases to that 5th term. And then you're going to put pluses in between. And now let's evaluate. Ready? So x to the 5th times negative 3 to the 0. This is just a 1, so this is x to the 5th. Plus 4 times x to the 4th times negative 3 is negative 15x to the 4th. And then 10 times negative 3 squared is 90, x to the 3rd. And then here we've got negative 3 to the 3rd is negative 27 times 10 is negative 270 times x squared. Plus, and then 5 times negative 3 to the 4th, that's going to be a positive what? 81 times 5. Let's see, 81 times 5 is going to give us 405 times x to the 1 plus, and then negative 3 to the 5th power is negative 243. So that's how we can expand out something to the 5th power. And then lastly, if I wanted to find the 3rd, term in the expansion. So here's what I want you to remember. We're just looking for the third term. So when we're looking at the binomial triangle here, okay, I want you to look at this. We're just looking at the third term in here. So if this is my degree of 6, here's 1, 2, the third term. So we're going to just take that coefficient, which is 15. And if it's the third term, remember, this would be our first term, which is in this case 2x. So we're going to go 2x and 3. This would be 2x to the 6, 2x to the 5. This will be 2x to the 4th. So we're going to put a 4th power here. And then this 3 would have been 3 to the 0, 3 to the 1, and this would be 3 to the 2. So we're going to put a 2 power here. So that's how we're going to find that third term. And so we get 15 times 2 to the 4th is 2 times 2 times 2 times 2, which is 16, x to the 4th. And then 3 squared is just 9. And if I multiply them all out, 15 times 16 times 9 is 2,000. So 160 times x to the 4th. All right, so what is the binomial theorem? The binomial theorem says, hey, if you've got any two terms to an nth power, that we take a first coefficient from Pascal's triangle and we multiply it by the first term to the biggest power times the second term to the 0 power, and we descend on the first terms from there, and we ascend from the second terms from there. All right, that's all we've got for today. See you back in class.